This is Official Nerd Business. Hello nerd boys and girls, welcome back to another episode of Coding in Python and Cracking Euler Problems. Today we're going to look at Euler problem number 4. I've already created a base template file with our description up top, largest palindrome product. Here's a list of parameters, which is only one, as we'll see in the problem statement. A palindromic number reads the same both ways. This goes for any palindrome, by the way, not just palindromic numbers. To give an example, something about palindromes has always been very fun to me. You have the word race car, and if we type that backwards, so that's an R of the back, and then an A, and then the C, the E in the middle, another C, an A, and an R. Hey, what do you know? It says race car twice. So this is a palindrome. It's written the same way whether you come from this end or whether you start at this end. Excuse me. It's the same word both ways. And we can have palindromic numbers as well. If we look at this number, which I've just pulled out of thin air, but it's a valid number, and it's a palindrome in that it is the same 125 to 1, 125 to 1. So the challenge here is to find such numbers. The largest palindrome made, and here's an example from two-digit numbers, is 91 times 99, leading to 9009. Find the largest palindrome made for the product of two three-digit numbers. So that's the one parameter that we're putting in here. How big a number we're gonna try, the number of digits in our number. So there's the problem statement, and here is your default run code. And I've already defined one function for our first attempt, and I explicitly say first attempt here because you can. If you take a moment to look at the problem statement, you can already see a brute force approach. This is simply running from 100 to 999, and inner loop doing the same, and then checking if that product is palindromic. But you can also immediately guess that we can do better than simply that. So there will be another attempt, which hopefully will run a little bit faster, which will be more interesting than just brute forcing it. That brings me to a point I want to discuss here, and that's timing our solutions. I want to make an addition to our to the program that runs our Python files, our Euler files specifically. We can run these on their own, which is fine, which I'm going to leave intact just as is, but that won't have timing info. And I want to edit our main py to also be able to time it. So this is now able to list our solutions. If I run this, we get a list of all the Euler problems currently in it. Number 4 is already shown, but it doesn't have any code to solve it yet. I can run it. And we want 3 digits, and it returns none. It doesn't have a return value specified yet. But I want to be able to see timing info here. So when it runs, it'll have a prompt of running solution, and then the answer, and then finding solution took X seconds. So that's what we're going to add to this program before we're going to switch back to actually solving the Euler problem itself. To see timings, we first need to import the actual time module. There it is. And then we're going to jump down to the bit of code that runs our, that's this bit. This actually runs our Euler problems for us. So above it we're going to look at what time it currently is. So t is time.time. This looks in the time module for the time function, which is the current time, and we could print this. I'm actually kind of curious how this is stored internally, so I might just have a look myself. Let's say we want problem 1. Upper limit is 1000 for this one. It's just a very big number. I think it's the number of seconds and milliseconds since January 1st, 1970, the Linux epoch. That's usually used when you see this sort of numbers. That's probably what's beneath it. So that's that. And we don't want to print the time itself. We do want to print some later challenges might take a couple of seconds before they return with an answer, so it's nice to see that it is actually running. How shall we call it? Program. Why not? Here the solution is printed. Let's just give it a bit more space, and again new line, and here we're gonna say how long it took. It took this many seconds. So here we have a string, and this string has a weird set of parentheses within it, and these curly braces are replaced by the calling the format on it by whatever we specify as arguments in the format. So let's replace it, and that's, again, we're going to look at the current time minus the time value we stored earlier. So here the format function has one parameter, namely whatever is left after subtracting the t from the current time, and that is placed back into the curly braces and printed on screen, if I did not make any typos. It compiles, so that's a good sign. Let's see, largest prime factor. Oh, this had this one very weird. Let's just type in a number. That was awfully quick. We wrote some good code there. Let's see if we can get some timing differences. So let's have a look at attempt 1, attempt 2, and attempt 3. We are currently running attempt 3 on problem number 1. So if you run number 1, 1000, this actually took some milliseconds. 0009. Let's look at attempt 1 because that was a lot slower. Let's rerun this. Excuse me. I misclicked something. Number 1, 1000. This is an order of magnitude slower. No, it seems 0009 or 01. Nah, this comes pretty closely, but as you can see, you can actually see differences in timing this way. Apparently, I think we will see a bigger difference if you run it for bigger values. But for now, we can see that timing of our solutions work, and I think if we're going to look at Euler problem number 4, that is going to be a factor. So let's first attempt brute force. Where we just let's see our upper bound here. We get a number of digits. So if we get a 2, we want all the numbers between 10 and 99 for instance. So we can do 10 to the power of whatever we get minus 1 up to, but not including 10 to the power of the actual number. Because if this is a 2, then we get 10 to the 1, which is just 10, which is the lower boundary of what we're looking at, and we'll get 10 to the 2, which is 10 times 10, which is 100, and we won't include that in our range, which is our 99 again. Okay, this seems to work. So let's define that range as exactly this. Our range object will already trim the last value that we said that we didn't need, so there we have it. Now let's see, we want to have a second loop doing exactly the same. As said, this is a bit of a naive approach. There's actually several points to this. Now we're interested to see what value we get when we multiply. In fact, we are interested in the string value of this, because we can quickly see if a string is a palindrome. We can simply do this. If m is equal to, this might take some explaining. M is a string, but it's a string in Python basically is a list of characters. So we have whatever characters are in here. This is a number, say it's 953, and we have a 9, a 5 and a 3. We make that a string, and now we have a list containing a 9, a 5 and a 3. So we compare if that is equal to, and here is a list slicer, an indexer. You can specify portions of a list. You can have a starting number here and an ending number here, but these are now left to their defaults, so that's the start of the list and the end of the list. And you can have a step parameter which specifies every second element or jumps of 5, or well, it also takes negatives, and in that case it starts at the end of the string working its way forward. So basically we're comparing the one list to the same list reversed, and if those are equal we have a palindrome. So what should we do with a palindrome? Well, we should first have a maximum value set to 0, and we should also check that if whatever we currently have multiplied is a palindrome, and that integer value of that palindrome is bigger than what we had previously, then we set our maximum to be this. Eventually this will result in finding the largest palindrome, or we will return it. Now, will it blend? We have 4, we want 3 digits. It took us 1/3 of a second to find the number 906609. I've already solved this problem. I've already got the green check over at ProjectEuler. I can tell you this is the correct answer. But it took us nearly 1/3 of a second. Can we improve on that? Well, we just might. There's a couple of things that you can easily spot here. We are looking for the highest multiple of something, which means that running through these lists backwards It will vary probably. If we start at 999 times 900 something else and we find a palindrome, there will not be a product bigger than that lower down on the list. It's with smaller numbers in the multiplication. So we can start by reversing this order. Let's take basically the same approach, but reverse this order. So we want this to be our second argument, this our first, and we can specify an order in which this runs through the numbers. So now we have the same range as before, but in reverse. Now for our second number, if this runs through all our 999s, then this is hit 900 times, then this skips to 998. If this one starts out at 999 again, we will do the same multiplication as we did when this was 999 and this ran to its second record. Though it isn't reversed yet. So as you can see, we are doing double multiplications, but not if we let this start at I and in fact let's make that +1. No, that's good. This needs to drop 1 though, because in this case, since this is now the first argument of our range, it would actually take 1000 and we want to prevent that. And then this would run almost entirely down, but not quite. Is this correct? This isn't. Yes, it is. Yes. And same goes for this one then. Just to be sure that whatever we find in our multiplication isn't dead last. And in fact, if we do find something, our first hit is going to be our highest hit, so we don't need to check for this. If we find a palindrome, we can simply return it. And we don't even have to bother with casting it back to integer. And as a failsafe, if we find nothing here that is palindromic, then we'll just return a 0 and none. None would be a better value, I guess. So let's rerun that. Our previous time was at 0.32. Let's say we want to run problem 4 with 3 digits. Oh, yeah, my mistake. I do need to call our new function. So let's try that again. Number 4, 3 digits. That is a lot faster. So there's the fun and timing. I hope you enjoy figuring out how we can speed this up even more. In fact, there's a challenge for the viewers involved here. If you go over to ProjectEuler.net and solve this problem, you will get access to an overview, and the overview shows a different method, a more mathematical method of finding palindromes. See if you can create an function called attempt3 that implements that method. That's all I wanted to show for today. I hope you've enjoyed it, and we'll see you back for Euler problem 5. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in ONB? Leave your thoughts in the comments. See you next time.